Swayam Prabha. Digital India. Educated India.
So in today's class we'll look at another building block of microprocessor, which is sequential logic circuits. Okay, we'll build some kind of a fundamental concepts around sequential logic, and slowly we'll develop the need for the memory elements which are built from your flip-flops. Okay, so that's how we'll kind of structure this lecture. So let's start with the you can see the slides. So the sequential logic basic concept will develop through an example. Okay, some of the problems in the domain can be solved without any use of microprocessor. One can kind of solve those problems directly by using some sequential logic circuits. Okay, and these circuits can also have some kind of a interfacing with some other mechatronic interfaces. Okay, so that's why it is important to understand what is possible with sequential logic. Okay, so that we can at times solve some of the problems with a lesser cost by using sequential logic rather than employing microcontrollers or microprocessors for such a task. Okay, so we'll develop this concept by using the example of a number lock. So this number lock has very simple primitive kind of a number lock, has 3 keys, and you are asked to enter the keys in some particular sequence, and then only the lock will open. Okay, the lock doesn't may or may not have other keys. Okay, so right now we consider lock doesn't have other keys. So can this problem be solved by combination logic is a question. So let's say we can try one attempt. Okay, so you have this kind of keys 1, 2, 3 as given here. Let me get my pointer right. Okay, so if they are pressed in the sequence 1 first, 2 second, and 3 last, then only this lock should open. Any other kind of a sequence, the lock cannot open. Okay, so we are given this kind of a problem to solve. Okay, now if we put our combination logic, okay, with the switches to kind of give 1 or 0 when switch is on, like one input is given to the to output of that switch and things like that. So we have these 3 switches. When the switch is pressed, that means the key is pressed, then the logic 1 will be there, and we use say AND gate. Okay, all the 3 switches are pressed, then I can open the lock. But now we do not get notion of sequence here. Like, see, if I press this 2 first, and then like 3, and then 1, okay, still my logic and logic will just kind of say that okay, I see all the 3 are pressed, and it will open the thing. So what is missing is the notion of sequence. Okay, that okay, I have pressed this first and then I am pressing the other one. Okay, that like what is previously pressed, that notion of the sequence is missing. Okay, so how do we handle such a kind of a scenario for designing circuits which will achieve this kind of a job? Okay, that is what is whole sequential logic about. That where combination logic fails. Okay, combination logic is only like given set of inputs, you have fixed set of outputs. Okay, and there is no notion of whether this is one key is pressed first or the other key is pressed first. That notion of sequence is not there in combination logic. Okay, so far we have seen in the last class, the combination logic circuit class, all the circuits are of that kind. So now how do we develop these concepts here? Okay, so that is what we will look at. So the question here is how to know if whatever key pressed is a first time you are pressing that key, or some key has already been pressed and you are pressing this key after that. Okay, so we need to know what was the previously pressed key, and beyond that, if this key is pressed, then we have some kind of a knowledge that is happening, which will further transform into opening or not opening the lock. Okay, so we need first notion, an idea that we need to remember something. What is that? We need to remember something what is like pressed before or something like that. Okay, so this notion of memory is there here, and then other notion that we'll need is the time, okay, or sequence. Okay, so just remembering is not sufficient. We need to know, okay, now sequence kind of a notion, or notion of time or sense of time, it needs to be there for this kind of problems. Okay, these are the two notions that we need: a sense of time and this notion of memory. Okay, so suppose we have that, okay, and we want to solve this problem. Okay, how do we go about doing that? Okay, how do we develop this now logic for say we are given memory, we are given some notion of sequence or time, then how would we attack or attempt this problem? Okay, so for this, then we need to define something called states. Okay, so we introduce something called states, so that we can introduce the notion of sequence for going from one state to other state like that. Okay, so that's how we need to define states. Okay, that's how we'll see how that can happen for this particular problem, and then this concept or these notions can be generalized to solve any other such problem by using sequential logic concepts. So we use clock for establishing some kind of a notion of time, and then we introduce this notion of states to say, okay, I need to remember now a previous state of the system. Okay, and then I can proceed for the problem. So this notion of state is for giving you this kind of a utility to use this notion of memory for solving such a logic problem. Okay, so how do you develop with this? What kind of a logic even can develop? How do we can develop? So think about this. Pause here for a moment, and then you can proceed to see the solution. So see, these pauses are important to develop something in your mind to attempt the problem. Even if you don't get the problem, is fine, but it is important to pause the video and think about and do something on your own, and then understand, then something will open up. Okay, that is a way the understanding happens. Okay, so as we say, like we have seen in the first class also. Okay, so you need to ponder over these questions. Can you define states and develop a state diagram for this problem? Okay, so how do we go about doing that? We pause and then proceed. So we develop these two states, like, okay, for sure we know that, okay, the lock is open or lock is closed. Okay, now what we want actually is that, okay, when the lock should open, when say some sequence is there. Okay, so sequence is what key 1 is pressed, then followed by key 2 is pressed, and followed by key 3 is pressed, then my lock should be open. Okay, so when my key 1 is pressed and it's the first key, that is right key, then I can change the state of the system. Okay, so somebody presses a key, okay, from reset point. Okay, it comes to the lock and it presses a key. Now if that key is right, okay, first key is right, key 1 is pressed and it is right, then I'll go to the second state. Okay, if that key is wrong in the first place itself, I'll go back to this closed state again. Okay, then if a person from that state 2, when state 2 is there, system is in state 2, and person presses the key 2, which is again the right key, then I move to the next state 3, Otherwise, if the key is not correct, then again I'll go back to the reset kind of a state. Okay, then so suppose key 2 is also right, and now I'm in state 3. Okay, at the state 3, if the key is 3 is pressed, which is correct key that is pressed, then I'll open the lock. That is a kind of a way we define the states, and we say that, okay, oh, this is how, like, the system will progress from one state to other state to other state when the right keys are pressed, and my lock will be open. Okay, so now how do we so complete this diagram? Like, okay, so right now this key pressed is correct key. If other key is pressed, then we need to kind of introduce that also in the state diagram. Okay, so any other key is pressed, you get to the reset state, which is closed lock. Okay, so this is how one can start developing the logic about these kind of problems. Okay, so you need to use judiciously this notion of state. What you define as a state is up to you. Okay, there are many different ways one can define what the state for a given problem is. Okay, and many different states. How many number of states that you want to use, you can use, and develop this kind of a state diagram based on which one can solve the logic. Once you have this diagram, so the way you have a table in the combinational logic, in the sequential logic you develop this kind of a state diagram. Okay, once you have a state diagram, then one can start writing a table. Okay, so how do we develop now a table? So let's say this state S1, S2, S3 are there as it is, like, we call them as a states S1, and then, like, we see, okay, there are these key 1, key 2, key 3 that are pressed, and we will introduce in the state diagram a notion of previous state. Okay, so that's how we'll use a memory. Okay, so memory is available. What do we use it for? To remember the current state. Okay, or the current state, so that it will become a previous state when you start doing the thing. So you remember the state of a system. Okay, so that you can take a decision for the future. Then so now there are some kind of a more nitty-gritty facts that, okay, assume all keys like buttons one press, they'll be remain pressed. Okay, so one can have this kind of a way, or if there is something button which is push button, then there is a different kind of a way things are coming up. So we'll assume right now that, okay, this is there, and there can be more complications. Say you can press and pop the button, okay, like keyboard logic. Okay, so these are all more and more nitty-gritties. We don't worry about that right now. Okay, so our focus is to develop these ideas of defining states and solving the problem by using states, and then, like, how do you go about solving that problem is what we are looking at here now. So how do you develop a state diagram is what you need to focus on. And pause here again, you develop your own state diagram. The table of we have already developed the state diagram. You develop a table around it, saying that, okay, key 1, key 2, key 3 are the 3 inputs, and state previous state is another input. Okay, and then what we want as a current state. Okay, that is a kind of a table that we need to develop. Okay, so you can see here the key 1, key 2 and key 3 are the 3 inputs, and previous state is another input, and next state is the output of the system, output of this logic table. Okay, so you remember your combination logic has always some inputs and some outputs. So here inputs have this additional input which is based on the memory. Okay, this is a previous state as a memory here. Okay, so now say for example, now key 1 is pressed and you are in state S1 and correct key is pressed, like, from the reset. Then you go to state S2. Okay, then now key 1 is pressed and key 2 is also pressed there, like the next key is pressed is key 2. Then you are in S2 state, then you move to S3 state. Okay, so like that you will have this logic developed. Okay, so all the keys are pressed and you are in state S3, then you are in open. So now if the keys are pressed and in some other kind of a sequence, then like you will have this next state will always be S1. Okay, so any other kind of a combination of previous states and the keys would lead to state S1 as a next state. Okay, that is how we define this complete truth table for this sequential logic. So the first step is about developing the state diagram, and after the state diagram is developed, then you introduce this previous state as a memory based that is what we remember in the truth table, and then you move on to developing the complete truth table. Okay, and then once you have once you have this table, you can use Carnot map or whatever ways to get your outputs expressed in terms of inputs, and then you draw the circuits. Now how do you draw the circuits? We'll see that later. Okay, how do you kind of use this memory notion? For that you need some kind of a logic gates, or which are having this memory notion into them. Okay, so that is what we'll worry about. So for example, now the states can be these are like some right now these defined as some kind of abstract thing that they need to be coded into some kind of a binary numbers. So say I will say 0 0 is my S1, 0 1 is S2, and 1 0 is S3. Like that I can define this kind of a 3 states. Okay, and then so you can have then logic developed based on this, and then you can do your output expressed as a function of inputs, and so on and so forth. All the things can happen that way. Okay, only thing right now we are kind of not so clear about is how do you introduce this notion in the circuit? What is the element in the circuit that will require to introduce this previous state notion? Okay, so we'll see that in a minute now. Okay, so how do you create memory is a basic question here. Okay, so what gives you memory in these digital circuits? And the simple kind of a way to create memory is use feedback. Okay, using the feedback in digital circuits will give you some ability to remember state. Okay, how does it happen? Very simple. So you have, say for example, you have these two inverters, and then this value you are giving as a feedback here. Okay, so this value, say for example, this value is 0, this value is 1 here, this 1 is getting as a feedback, and then this one is again producing 0 here. That means this is like a stable state here for this circuit. Okay, circuit is stable, holding this value 0 here and 1 here. Okay, so as long as the power is applied, this value will be held. Okay, now we can kind of introduce the way to remove the value and store new value. Okay, so how do you get this new value? So you break the path. Okay, so this is a, say, remember kind of a switch here. So you open the switch and put like a new value into this circuit, and then moment you close this switch, that new value will be remembered now. Okay, whether it is 0 or 1 doesn't matter. If it is 1 here also, the same thing happens. Okay, that is a stable circuit. Okay, but now we cannot do this switching on and off manually. Okay, so that's where one uses electronic switching, and so this is a way like load and value and remember the value. But this manually we cannot do this, so that's where like you introduce these other gates to have electronic switching kind of action going on. Okay, and that's where the RS flip-flop comes into picture. Okay, you might have, as a prerequisite, you might have gone through some of the RS flip-flop literature and D flip-flop literature, and you may know how they are working. We'll just touch upon some of the aspects of them. Will not get into a lot of details about them. Okay, so if you want to, you can brush up that knowledge again. But the fundamentally from microprocessor perspective, that is the first kind of a the basic memory element into the system. Okay, so so now this way RS flip-flop works is very simple actually. It has these two NOR gates connected with this feedback. This is a recall for the of the NOR gate. With this truth table, one can figure out like, okay, with different inputs of R and S, what is the output going to be, and what is going to be the stored values. Okay, like that one can kind of get the sort of truth table done for this RS flip-flop. And a simple way to think is that this NOR gate with one input 0, it acts as an inverter with respect to other input. Okay, one input is 0, then with respect to other input it is acting as an inverter. Okay, so one input, say A is 0 0 here, so B is acting as B to Z, or B to this output for the NOR gate is acting as an inverter. Okay, or as a NOT gate here. Okay, so say both R and S are 0, then we have exactly, if you redraw the circuit when R and S are both 0, and this is acting as an inverter, this is acting as also as an inverter, then this simply becomes our two NOT gate connected in series and having a feedback kind of a circuit. Okay, so this is again same concept as what we had for the memory. Okay, before we had seen before, when R and S are 0. So when R and S are 0, this circuit is going to remember the values which is stable values, and to introduce new values you will change the value of R or S. Okay, that is a simple kind of a way one can understand this RS flip-flop or RS latch. Okay, so we'll not get into too many details about it, but one can brush up and see how this values of change can cause changes in the value of outputs is Q and Q prime. And when R and S are 0, then whatever value is previously there, it will be remembered. Okay, that's how one can see this as a memory. So these are some additional controls one can introduce now to enable this flip-flop or disable it and things like that. So then the changes will happen only when this is enabled. Okay, then one can add further the gated RS flip-flop. Okay, where you now use this clock to introduce this clock in the circuit to say that, okay, the changes will take place only when the clock pulse is positive. Okay, see why this is introduced is basically there are so many kind of transistors that will be there now. So see, so many even this RS flip-flop itself, if you go to the circuit level, it will have so many CMOS kind of transistors that are working, and we want these timings to be happening or these changes in the state from one RS flip-flop to the next state. They need to happen in some kind of a controlled manner. Okay, they should not be like a runaway kind of a manner. They should switch. Okay, so that's why this is introduced here, to make sure that when this pulse goes high, then only your switching is going to happen here. Okay, so so then you connect these latches together with additional kind of inverter here to make sure the states changes that are happened in this circuit will get reflected to the next circuit only when the next kind of a clock cycle comes. Okay, so like that you introduce this gated RS latches along with the clock and this now inverter also here. So so when this is acting, then this is disabled, so it will prevent the changes to rush into this. Okay, so once all these changes have happened here, then only this when clock goes whatever high or low, this will get enabled, and the changes from here will be passed onto this latch, and that will happen like that. You do on the clock cycle, then the things are more robustly achieved when we have scaled kind of versions of these circuits coming in place. for microprocessors. Okay. Now we now add one more kind of a modification. You might have already seen this called a D flip-flop, where you put an inverter into RS flip-flop. Okay, so that R and S here, so this inverter is put, if you see, is on the gates here. Okay, so their output, these are AND gates. So this will make sure that this R and S cannot be both 0 when clock is enabled. Okay, and this storing value will happen only during this clock cycle. Okay, so see, this this will make sure this you can just kind of do a little bit an analysis and you'll find out that, okay, that R and S cannot be both 0, and then these changes will happen only during clock cycle. Okay, so see, when the clock is disabled for this part, then R and S are going to be 0, because these are AND gates here. Okay, so R and S are going to be 0. That 0, both 0 will store some value. Okay, but then this input cannot be both 0. Okay, so either 0 or 1 value is going to get stored, or like, no, it is going to get stored in based on the input that is given at D. Okay, so that is what is this inverter is doing here. Okay, so, and that's how this D flip-flop is getting built. So with this we get this D flip-flop to remember. So this is like Q plus state will be coming out here, though this is Q plus is after one clock cycle. Okay, this plus means after one clock cycle. So if this input is D, after one clock cycle, that input will be reflected on this Q here. Okay, so that is how this D flip-flop will work, and this is particularly negative edge triggered D flip-flop. Okay, so there are many variants of this flip-flop, but for our case right now, what is most important is this memory notion that we are talking about. Okay, the notion of memory comes now here, that a state will be remembered for one clock cycle. Okay, and then the next state will be like, the changes of the state will happen after one clock cycle. Okay, so at any point, if you say, okay, this is input I am giving here, but output here is going to be previous state at any point of time, this output will become a new state only after one clock cycle gets passed. Okay, and after this is changed to say, like, new value, and my value is changed here, this doesn't immediately change. So this will be changing only again after next clock cycle. So previous value will be remembered here till that time. Okay, so that's how this notion of memory is introduced here. Okay, so in this D flip-flop. So these are like some variants here, but and some kind of a case for you to think about and consider how this input changes to the D flip-flop. This D is input, and how the outputs will change and how the states will change when the clock changes. So think about this, and then we can now put together these D flip-flops to get different kinds of circuits. The way we had some kind of a combination logic circuits, we have now these 4 bits. Say, for example, this ring counter. So we want to count these numbers here, so we are putting some kind of a these D flip-flop in series, and like looking at the output of this flip-flop as the clock ticks. Okay, and this the output of the last one is again given as an input to this first one. Okay, so under this scenario, like how this ring counter will work as the clock ticks. Okay, so if we start from say 1 0 0 0 state. Okay, so let's say somehow we have got this state inside here. Okay, so after one clock cycle, so they say this is 1, this is 0, this is 0, this is 0. Okay, after one clock cycle, this 1 is going to get passed on to this. Okay, so this will become 1. Okay, what will come here is what is here. What is here is the output of this 4. So this 0 is output right now, like the fourth, like last part was 0 here. That will come as a next state. So this is how, like the next state will be 0 1 0 0, and next state will be 0 0 1 0, and things like that. Okay, so so this is one of the ways one can build these kind of a counters. Okay, so these counters are very important in microprocessors, microcontrollers both. So there are many variants that can be possible. You can look at some of these so like a variant like these. Then you can introduce a NOT gate in the feedback, okay, to enhance the number of states that are represented. So say you think about, for example, for this here, if you run through this time, like as a clock ticks, what are the states that will be represented by this Johnson counter, so to say, when we start at the state 1000. Okay, so now this final output is going to get inverted, and it is going to come in the front. Okay, so that is how it will look like, 1100. Okay, as a second state. Like that, you'll be able to kind of see all these states. So you can with this kind of a thing, you can see that, okay, we are able to now represent more number of states as a sequence in this counter. Now the question is, suppose we want to count, okay, 3-bit, for example, okay, but we want to count in a way that, okay, we want the output to be binary 0 1 2 3 4, like that, up to 8 or 7 rather. So the 3-bit up counter, okay, 1 2 3 4, it will count 0 1 2 3 4, 8 numbers it will count. So these are binary numbers. Okay, so how do we develop such kind of a counter? Okay, so again we use the principle of state here. Okay, so this is how, like the sequential logic design needs, like the definition of states, and once you define states, then like the problem becomes very easy. That is expressed now as a combination logic problem, and then we'll see how we use now D flip-flops to get a circuit out of that combination logic table. Okay, so first thing here, to develop a state diagram. Okay, so you do that, pause here, do the state diagram development, that, okay, if I am state at state 0 0 0, then what will be my next state? So my next state will be 0 0 1. If I am at that state, what is the next state? Like that, I develop the state diagram. Okay, and you can see this simple state diagram will come up. So so there are no external conditions for transition here. Okay, you remember in our log problem, there are the conditions on the keys that would take us from one state to other state. Okay, but here there are no such kind of conditions. Okay, so there are no external inputs. So again we can develop then the truth table in the similar way. We don't have any other inputs. We are going from just one state to other state without any kind of a condition on any other kind of a key or any other input. So this say number, like say I say this number is C, first number is C, second is B, and third one is A. Now what should be the truth table entries? Okay, you can develop that. Okay, so see, now we have this C, B, and A are the present state. Okay, then the next state should be what? Okay, if the present state is C 0 0 0, then next state should be what? Okay, think about that. So if the present state is 0 0 0, next state I am going to is 0 0 1. Okay, so I'll write 0 0 1 here. So these are like the next states. C plus, B plus, and A plus are next states. Okay, so we don't have any other outputs here. Okay, in the previous case we had output of lock open or close. We don't have that kind of output here. Okay, so we just have these three outputs, and then we can complete this truth table. Okay, so you complete it yourself first, and then only look at what is done. It will open up some things for you. Some mistakes, small kind of nitty-gritties, that will get corrected. Okay, now we have generated these. Then we can use K-map or other kind of whatever techniques you want to use for for getting like expression for C plus as a combination of ABC. Okay, so I want to express C plus as a combination of ABC. These are because these are my next states. Okay, these are my outputs, and these are my previous states. Okay, so I would express them, and this next state are only dependent upon previous state. No other inputs they are dependent upon. Okay, so that's how I have. So I will express C plus as a binary or Boolean expression of ABC by using Carnot maps, or by using sum of products rules, or some kind of a way that you have learned in the past. Okay, so this is more like a development of Carnot maps, and I'm not going to get into how they are like written there, but we get finally this expression by using these K maps. Okay, you can pause here and go through if you want to revise your Carnot map and get these expressions. Okay, like that you will develop it for B plus also. Okay, so B plus is expressed as some kind of a function or Boolean expression of ABCs. So this it happens that this is not dependent upon C here, and the same way for A plus. Okay, so now the question is that these are the expressions for C plus, B plus, and A plus, and we want to now develop the circuit for implementing such a kind of expressions. Okay, by using now flip-flops, okay, or memory elements. Okay, so see now the new state C plus is dependent upon is expressed as previous state, some kind of a combination. Okay, so how will you develop such a thing? So this is what we want. Okay, the next state we want to be coming as a function of current states. Okay, so current states are available as so we use D flip-flop for this purpose. Okay, so how do we use that is explained here. Okay, so the way we implement the previous and current state using D flip-flop, so say some input A is current state is available here. Okay, and I want the state after one clock cycle to be given as here. So I use now, depending upon the variables I have, are 3 states I need to define. Okay, so I need to use 3 D flip-flops. One is for A, one is for B, and other is for C. Okay, so these are 3 D flip-flops I'll use, and for these D flip-flops at any point of time the current state is available at the output here. Okay, and I use that state and then produce my A plus as per these relationships that I have produced already. Okay, so if I do that, then these circuits comes up. Okay, and then this becomes like my circuit for 3-bit up counter, which will be counting exactly the way I want binary numbers to kind of get counted. Okay, 001, 000, 001, 0010, like that it will come up. Okay, so this is how these circuits are to be developed. Okay, and in the same way our problem of the key lock, okay, the lock problem that we discussed can be also kind of converted into circuit now. So what we need to remember is the state. So we need to define for the state some kind of a binary representation, previous state and new state, like that. It will come say if your state is A, B are 2 numbers that are defined, then you'll have A plus, B plus coming up when the previous state and the new state are expressed in your truth table. Okay, so you can do that exercise as a homework. Okay, so this is how we go about developing these counters or sequential logic circuits. Now we want to build memory. So we'll talk about a little bit about memory. So memory will use now say 3-bit memory. We need to remember 3 numbers. So we need like the 3 D flip-flops to be combined together. Now how do we kind of put value in the memory, and how do we get the value out of memory? So that is what is more nitty-gritty to talk about. So we use this clock which is going to the D flip-flop judiciously to see, okay, when I want to store my value in the memory, when I want to get value out of the memory, how this is done. That's what we'll see in the next class, and then we'll see some of the putting together now all these elements, how we can kind of build some small primitive microprocessor to get you just a feel of like how things work in general. So maybe we'll stop at this point here and continue in the next class. Okay.